Hello, this is Mrs. Hogan. I am going to talk about the simple machine screw in this video. You may be used to seeing screws like these, but there are also other things considered to be a screw simple machine, like the nut that keeps the screw in place. It also has threads on the inside, so it is considered a simple machine screw. And also a spiral staircase can be considered a screw. A screw is just an inclined plane that's wrapped around a cylinder. See, here's a good example that you can see this inclined plane, if it was wrapped around, what it would look like as a screw. The distance between the two threads here is called the pitch. Most screw simple machines have two components, the path and the wheel and axle that is used to create that rotary motion. To put a screw into wood, you would have to go get a screwdriver, and that would be that wheel and axle. As the screw is turned, it moves straight down or coming back up, depending on which direction you are turning the screw. Alright, so a screw is going to have a really large mechanical advantage depending on how large the screwdriver or wrench that you're using. But most of that force, of your force effort, is going to be lost to friction. But if you think about it, you want all of that friction there, because when you're putting a screw into something, you're trying to hold it in place. To find ideal mechanical advantage for the screw, you're going to use the same formula you've been using in the other simple machines. Ideal mechanical advantage equals distance effort over distance resistance. Distance effort is one rotation of the effort arm, which is considered the circumference. What that means is you're going to find the radius of the wrench that you're using or your screwdriver. You're going to find the radius of the actual handle of the screwdriver, and you're going to find the circumference using that radius. So the circumference is 2 times pi times r, which is the radius. And that is going to give you the circumference, because what we're trying to find is one complete rotation of the screw. So your hand would be at the end of the wrench going all the way around to get one complete rotation. So the radius would be the length of that wrench. Or your hand would be on the outside of your screwdriver, and so finding the radius of the handle of that screwdriver, you can find the circumference, which would be the distance that effort would go all the way around. The distance of your resistance is the linear distance traveled during one rotation of the effort arm, which is considered the pitch. So when you are going one complete rotation with your screwdriver or with your wrench, the screw here is going to travel from one thread to the next. So when it goes one complete rotation, it's going to go down or it's going to go up one thread to the next in one rotation, and that's called the pitch. In this example of the jack screw, notice our distance effort is 2 times pi times L. L being my radius, it's the length of the handle on the jack screw. Then my distance of my resistance is going to be the pitch, the distance between each thread. By looking at this example, you can tell that my ideal mechanical advantage is going to have a very high number. But there is so much friction for these simple machine screws that the actual mechanical advantage is much lower. So the efficiency of a screw is going to be very small. In some of the problems that you work, your pitch will be given to you. Other ones are going to give you thread information. This is an example here of the thread information, and this one here. The main information that you're looking for, though, is right after the diameter, it says threads per inch. Again, you've got your diameter, and then you have your threads per inch. This number here is what we're wanting to look at. This means that I have 13 threads in every inch. So if I'm trying to find the distance between each thread, then I'm going to say it's 1/13 of an inch, or in this case it would be 1/20 of an inch. And then I could go ahead and divide out that fraction to figure out the distance between each of the threads. Or I can put it in my equation as an actual fraction, as 1/13 of an inch, or 1/20 of an inch. Looking at this screw right here, we have our information, the diameter, and then the number I'm actually looking for, the 20. This means that when I do one rotation, a full rotation with my wrench, or a full rotation of the screwdriver that I'm using, my screw is going to go down 1/20 of an inch. If I use a wrench that is 8 inches long, then I can plug it in and find my ideal mechanical advantage. So 2 times pi times 8 inches divided by 1/20 of an inch. And that's going to be approximately 1,000. So you can see that this is a very large ideal mechanical advantage compared to the other simple machines we've been working with. To find my AMA for a simple machine screw, it's again the same formula you've been using before. AMA equals force resistance over force effort. So it tells me here that my force resistance, we're assuming it's whatever it's being screwed into, it's the resistance of that material, is going to be 1,200 pounds. So I'd put that on top. And then my force effort is 35. So 1,200 divided by 35 equals 34. So now in this example, when using an 8-inch wrench and 35 pounds of input force resulted in 1,200 pounds of output force, what is your efficiency? Because it's a screw, I'm expecting it to be pretty low. My efficiency is AMA divided by IMA times 100. So 34 divided by 1,000 times 100 is going to be 3.4%. Not all screw efficiencies are going to be quite this low, but they are going to be lower than the percent efficiencies that you've been getting for your other simple machines. Alright, so now I think we're ready to go see what I found in the garage. Alright, now I have a screw to show you. Alright, so here is a screw. I tried to find a larger screw so that we could easily measure it. Alright, so we're going to look at this section here. I've kind of darkened it so that you can see it better. So first, the distance of our resistance is going to be from one thread to the next. Because when this rotates, an entire rotation revolves around one time, then it's going to go into whatever you're trying to screw it into. It's going to go down this distance, one rotation. So let's go ahead and measure that. Right? And sometimes it's easier to go from like just 1 inch in the middle of your ruler because sometimes you lose some here at the end. So looking here, you can tell that it's 1/8 of an inch between the two. Or if you're given a full inch, how many is that? We're going to count. 1, 2, 3, 4, 5, 6, 7, 8. So you can tell that there are 8 threads in an inch. And just by looking at it too, we could tell that it was 1/8 of an inch distance that it's going to go down. Alright, so whenever we hook this to a tool, let's use this one here. I tried to find one with a really good mechanical advantage. We need to find the circumference because whenever I am putting a screw into, say, wood or whatever it is that the medium that I'm putting it into, one full rotation, my effort, is going to be the circumference of this circle. So to find circumference, it is just going to be 2 times the radius times pi. So we need to find that radius. So the radius is going to be from my center point here, to where my effort is going to be. So my effort is going to be on the handle here. I'm going to go to the outside of this handle. The outside of the handle is about right here. So that is 5.5 inches. So the radius is going to be 5.5 inches. So to find the circumference, which is the actual distance that my effort is actually traveling, okay, so the effort, if I start here, go all the way around, that is the circumference. And that would be my distance effort. All right, now let's use those values to find the IMA of that screw and wrench combo. So my IMA equals distance effort over distance resistance. My distance effort was 2 times 2.5 inches, and my distance resistance is 1/8 of an inch, which equals 15.7 inches over 0.125 inches. When you take 15.7 inches divided by 0.125, you get 125.6 as your IMA. And of course your inches are going to cancel out. This is a very high IMA. You'll find that your screws will have very high IMAs, but most of the time the AMAs will not be quite as high.